Okay, so we'll finish this week's lectures with a bit of discussion of a different way of doing evaluation, particularly uh, evaluation as a relation. So I'm going to come back to this part, but I'll skip down to the inference rule version. So um, just so we can sort of see what we're doing. So in this example here, we're talking about evaluation of arithmetic expressions as before. Remember, we defined a val, which is a function that takes an arithmetic expression and returns the natural number, which is the value of that expression. So the aim here is sort of something similar, right? We want to define a relation between arithmetic expressions and natural numbers. So it's a binary relation. And a pair of an expression and a number should be in the relation if and only if the value of the expression is that number. Okay, so in this notation, they're using this slash slash to denote the relation. So you should read this as this expression has this value. Okay, so it's a pair. So as before, we could say, well, then the value of a numeric constant expression is just the number that's in the thing. So a num n is related to n, is the way to think of it. Okay, so then for the other ones, you've really got a recursive sort of situation, right? So a plus e1, e2 is related to some number, which is the sum of the values that are related to e1 and e2. Okay, so this plus here is just a meta sort of plus. It's in the notational world. But this is basically saying if you can show that E1 is related to N1 and E2 is related to N2, then you can conclude that A plus E1, E2 is related to the sum of N1 and N2. Okay, and the others are similar. Okay, just with a different operator. So in the inference rule setting, this is if I need to work out whether an expression has a particular value, I can try and derive a proof using these rules, and eventually everything terminates at the anum axiom. If I can do that, then I've shown it. If I can't, then I haven't shown it. But it's different from a computational definition, which is what we saw before. We'll come back to the difference between computational and relational approaches at the end of this lecture. So if I go back up to the Koch definition of this, so the long form is this one up here. So we're defining A val R as an inductive relation, so it's a prop. And you can see from the arguments here that it's a relation between arithmetic expressions and natural numbers. So that means that anywhere A val R appears down here, it has two parameters. One is an expression, one is a number. And then we have one constructor for each of the inference rules. So for example, in the first one, we have that A num n is related to n for all n's. So it's not a single axiom, it's really an axiom schema, we say, because it's an axiom for every value of n. And the other ones are the other constructors have more parameters because they've got to talk about the subcomponents of an expression. So for example here we're saying if the pair E1N1 is in the relation and the pair E2N2 is in the relation, then the pair A plus E1 E2 N1 plus N2 is in the relation, and this plus is just the normal Koch natural number addition. Okay, the minus and the mult are similar, but they have the different operators and the different constructors, obviously. Now, one of the points they make here is that it's often a bit hard to read these definitions because of all the repetition of this A eval R. So like in the inference rules, they define a notation with the backslash backslash that says E backslash backslash N is the same as A eval R E N, right, with a bit of precedence and associativity to make it sort of work nicely. You can also do this sort of, so this version up here relies on you defining a thing in the long-handed way first and then writing a notation. So then from then on you can use the notation. But often it's nice to use the notation in the definition itself, which is what this reserve notation does. So it basically says that there is going to be a notation that's going to be used for this, and the where clause of the definition actually says what it means. So this has to be part of the inductive definition as the where clause, rather than a separate notation like up here. So here you can see that the definitions of the types of these constructors are a lot easier to read now because they're using the notation instead of the name A eval R. But otherwise this definition is equivalent to, is exactly the same as the one above. Okay, so if we have this definition, then we essentially have a second way of thinking about what the meaning of an arithmetic expression is. So in this case, we have a way of reasoning about the relationships between expressions and values and numbers. And we have the other one, which is the computational one, which was the function A eval, which is just expression in, natural number out. Okay, and these are different definitions. If we go back, skip over all the inference rule stuff, but ideally we would want to know that they're the same in some sense, right? So here's a theorem that says if A and N are in the relation, the A eval R relation, then it must be the case that feeding A to the function gives us N, and vice versa. Okay, so this proves that these two definitions are equivalent, right? That you can sort of use them interchangeably depending on what the circumstances are and what's more convenient. Whether you need a relational style or whether you need a functional style. So this proof, I won't go through in detail, but is just using things that we have seen before lots of times and just casing out the forward direction and the backwards direction, and then casing out the different kinds of things. So for example here, the thing we've got in the hypotheses is the relation that A is related to N. So the induction is being done on that relation. So that's inductive proposition. So we get one case for each possibility of the relation. And the proofs are pretty straightforward, either follow directly or just using the inductive hypotheses. And the other case, the other direction, the induction is on the expression A. So we need to case out all the different possibilities for what A might be, and that's why we end up with 4 cases for the forms of our arithmetic expression. And then the proofs are basically use the constructor that's appropriate and then use the inductive hypothesis in each case. Okay, so this is pretty straightforward based on what we've seen before. And then they say, well, now, but we can remove a lot of the repetition here. So there's a few cases here that look very similar. So like these 3 cases up here are basically the same. They are the same, right? These cases down here are not exactly the same, but they have the same structure. For example, apply a constructor and then do these steps is what the last 3 are like. So this version down here is saying do the proof in such a way that you can avoid the repetition basically. So let's go through how this works. So one technique for this that's a bit, well, that you'll find is frustrating is if I run this, it will run all the way to the next dot. So we don't really see anything happen. So if I put in a dot here, we can sort of see the intermediate state, right? So this is our beginning position. So if we do a dot here, we'll stop there. So you can see now we've got 4 cases for the a-val side of things, right? Or based on the induction on the relation. And if I go, let's just do this a bit. I go into one of these, that one's going to be pretty boring, right? So that's going to be a reflexivity. I go into this one. So one of the things that you've got going on here is there's a few variables like n1 and n2 and so on. And often in this sort of situation, it's easier to see what's really happening by basically using these to rewrite the goal. So get rid of the n1 and n2 in the goal and just replace them with these a-val expressions. So you could rewrite with these IHs, but one way to do it is to do the subst. Right, and so that's our first use of subst. So that's basically just gone and found these 2 hypotheses, and it's rewritten the n1 and n2 away and then deleted the hypotheses. So you'll see everywhere n1 and n2 appear. Now you get a-val e1 and a-val e2, which is a lot simpler, less variables to worry about. And then the simplification here gives us the answer. So reflexivity is going to do it. Oops. And because that is going to work, because that's going to work for all of the next 3 cases, we can combine it all together. So in this case, what we're doing is doing a subst. Now notice that the first case doesn't need a subst, but doing one is not going to cause any harm. And then we can do reflexivity to finish off all the cases. So that gives us a nice, short, simple proof for all 4 cases, and we don't even have to sort of realize that there are 4 cases there. The other direction is similar. So in the proof up above here, we had these sorts of patterns, okay? So the starting point is induction on this thing and a simplification and an introduction of everything. So let's stop there. Okay. Now if we have a look at the next level, just to see what's here, the next thing we want to do here is apply, according to our proof above, is apply EA_num, right? Which we can do, but we can also do constructor. And that will find the appropriate constructor. No, it won't. We have to do a substitution first, sorry. Okay, because the constructor that the a_num constructor requires that the 2 numbers here are the same, whereas without doing the substitution, one's n and one's n0, so they're not necessarily the same. So the subst will do that, and then constructor will solve that because that matches the a_num, the EA_num constructor. Okay, and it turns out that doing that for all of them is what you want, because the first step in each of these is going to be using the appropriate constructor, and substitution first to just make things look in the right form. So we can do that. So that gets us to a point where a lot of things have been simplified away and so on and so forth. If I go into the first one of these, what what do we need to do to this? Well, we basically need to use the, let's see, yeah. So one thing to notice is, if I go back here, right, so we've got 6 sub-goals. Why are there 6 of them? Well, basically, the first part of this proof has already solved this enum case up here. So it's gone. And then the constructor thingy has created assumptions that we need to prove for each of the constructors. And because each of the EA plus and EA minus and so on have 2 assumptions, we end up with 2 times 3 because we've got 3 cases still left. So we get an A1 and an A2 for each of the 3 cases of the plus, minus, and mult. That's why there's 6 of them. And the way to solve one of those is, so here, for example, we would say, well, okay, this guy, this goal, matches this conclusion of IHA1, right? So we want to apply IHA1, and then we're done. And then the second goal is going to use IAH2. Right, and the pattern continues. So we'll use IAH1 for the first one and IAHA2 for the second one. And this shorter version basically combines all that together. So basically says, well, try using IAHA1. That might not work. So if that doesn't work, try IAH2. And we're assuming, we know for these 6 cases that one of these is going to work to apply, and then reflexivity will be able to finish them all off. So this version of the proof, if we continue with a semicolon there and get rid of all this stuff, this, you can sort of, if we stop here, you can see that every second one, the apply has done something, but IHA1 doesn't work for the A2 cases, so these ones haven't changed. And we haven't got an error because we've got a try that's stopping it from crashing out at that point. And then if we stop after the second try, you can see that now all 6 cases have been fixed. And so the reflexivity will now solve them all. Okay, so that's a really good example of how the tacticals and things like subst and constructor and so on can really make a proof much smaller. Usually though, it's easier to come up with at least a good chunk of the original proof first before you realize that this sort of thing can happen, because it might not be obvious that, you know, these 3 cases are all going to be very similar and so on when you're doing it for the first time. So often you write out the longhand version of the proof and then simplify it down using the tacticals. And as you get more experienced, you can do that a bit more in advance, but often at this stage, it's better to try and write the long-winded version of the proof and simplify it later, which is exactly what you have to do for the homework. So the the third homework question this week is the B eval R here, where you have to write the relation for evaluating a Boolean expression, just like we did for the A eval R. Okay, and you'll notice that the B eval R will have to use A eval R, because to evaluate Boolean expressions, you have to be able to evaluate arithmetic expressions in some cases. So that's question 3. And then the other 2 parts basically ask you to prove the equivalent of this theorem here, the A eval if and only if A eval R prime, for B eval R and B eval. Okay, so an analogous theorem holds for Boolean expression evaluation using the function or the relation. And so you can write that theorem and prove it. That's the first part. And the second one, 5 here, is saying we'll do the same thing as we did up here and try and take your long-winded proof and use the tacticals and automation and stuff as much as possible to try and simplify the proof down to be nice and small. Okay, so follow the A-eval style and you shouldn't have any problem, I don't think. Okay, so finally, let's just step back a second and think about what we've got here. So for A-eval and B-eval, we've proven or will prove that these are equivalent definitions. So there's one argument saying, well, why would you prefer one over the other? And in fact, if they're equivalent, usually the function one, the computational one, is preferred because it's more automatic. So if you've got an expression, you can just run the function to get the result of it, and that tells you the value or the meaning of the expression, whatever that means. The problem is, and that's deterministic, you're always going to get the same answer because we don't have any side effects and things like that. The relational one is a bit more unwieldy in the sense that if you've got some relational pair that you want to prove holds, you can't just run the relation. There's no such thing. You have to use the inference rules to sort of deduce whether this holds or not. You can't just run the function and do a comparison to see whether the answer is what you expected it to be. But on the other hand, Coq puts a bunch of restrictions on functions in this language. For example, they have to be total, so there has to be an answer for every possible input. And 2, they can't run forever, right? Now, in this language at the moment, we don't care about the running forever part. We might do that. We'll care about that for later on. But we do care about well, there must be an answer to return. Okay, so if we wanted to write take our arithmetic expressions and say, well, let's put division in, same form as the other operators, what do we do about A-eval? The problem is we don't know what to return when we do a division by 0. Okay, so here it's a division by a constant 0, but it might be some expression evaluates to 0 and then is used as the inner divide. So it's not obvious what to do about A-eval. We can't really do that, right? Now we could possibly say, well, let's make A-eval return an option or something that says, well, it worked or it didn't work, but then that's unwieldy because then each of the recursive cases has to check whether the recursive case worked or not, and if it didn't, propagate the not working to the next level, and it gets messy. Build nested options and things like that. Whereas modifying the relation is actually really easy because the relation, in other words, the inference rules, are only talking about cases that work. So you don't have to specify ones that don't work. In fact, that's the whole point of the relation. It's only defining the things that are in the relation, not the things that are not in the relation. So in this case, we can add this division one here with a similar form to everything you've done before. We don't want to add it like this, right? Because if there's a divide here, then that divide might not be defined in some circumstances when n2 is 0. So this form that they've written here is a particular way of defining division using multiplication. Right? So it's basically saying, well, first we have to require that the number we're dividing by is bigger than 0. And then we can also say, well, if we then have a proof that multiplying the denominator by something gives us the numerator, then the result of a division is defined to be that number that we can multiply by. Okay, so we don't actually do a division, we just use multiplication to define division. Okay, and this means that you can sort of get more power out of the relation because it doesn't have to worry about the cases that are not well defined. Okay. The big example we'll see later on in the unit next time is the language that we're defining will have loops in it, while loops, and while loops can be infinite. Some while loops just don't terminate. So if we tried to do a computational version of that, we couldn't do it because the computational function that's working out the meaning of a while loop would have to run forever. And Coq doesn't let us write functions that run forever. They have to be total. So, but we can do it with a relation that's similar to this style, which we'll see later on. Okay, so that brings us to the end of week 7. Week 8 we'll pick up with the rest of the IMP chapter. In particular, we'll add support for statements like assignment and loops and conditionals and those sorts of things. And part of that is we're going to need variables. So these expressions that we've currently got don't have any variables in them. So we'll add variables to them next time and think about what that means for evaluation. And basically it means that we have to keep some state around to tell us what the values of variables are when we need them. And that will involve extending what we have here a little bit, and then we can use that for doing the statements, the commands of the language as well. Then we'll have a full definition of what evaluation of these imperative programs means. Okay, so I'll stop there and talk to you next time.